Hello. This part is called Basic Thermodynamics. It's part of the Level 1 training for ClimaCheck system. And the idea here is that give you a better understanding of the thermodynamics in the background and the pH diagram and how that is used in the ClimaCheck system. So the pH diagram, anyone that has come across or looked at refrigerants have probably come across this pH diagram. The pH is pressure enthalpy, stands for pressure enthalpy, and the diagram represents the relationship between pressure and enthalpy for different refrigerants. So each refrigerant will have its own pH diagram. They will look pretty similar, but of course the pressures and enthalpies will differ. But the main they will look pretty similar for different refrigerants. The ClimaCheck system is using the information from this pH diagram in the background when it's doing the calculation. The pH diagram can also be used to represent or show the process of the systems we are measuring on. So I'll give you an example of that. Even though the ClimaCheck system is using the information and the actual enthalpy pH diagram is not displayed in the software anywhere, but we'll come back to why that is. So in the pH diagram, the refrigerant is in its liquid state to the left in the diagram. So this part here, from this saturated liquid line and to the left, is subcooled liquid. On the right side, you have superheated vapor. So the refrigerant will be in superheated vapor from this line and to the right. In between here, within this region, it's called the mixed region. And in here you have a mix between liquid and vapor. If you move in this diagram from the left to the right, you are adding energy to the refrigerant. Well, that's typically what happens in our evaporator and the compressor. We are adding energy. If you move from right to left, we are removing energy from the refrigerant, typically in our desuperator and in our condensers, we are removing. So then we move from right to left and from left to right in the evaporator and compressor. There are also lines that are called isotherms. These isotherms are indicate equal temperature. So one of these lines here, all the way here, you have a constant temperature. You can see that the pressure and the enthalpy is changing here, but if I keep to this line, I will have a constant temperature. In our system, when we condense and evaporate, as long as you have a non-mixed refrigerant like R104A or 22 ammonia, as long as we have a non-mixed refrigerant, we will condense and evaporate along these lines, so at a constant temperature. So if you're evaporating at a certain pressure, you will then evaporate at this constant temperature all the way up here until you have 100% vapor. Same thing in the condenser. At the higher pressure, you will condense at the constant temperature until you start have 100% liquid and you start getting subcool. For mixed refrigerants, like 404A, for example, you have a small change in temperature when you're moving and evaporating or condensing. So then you have what you call glide. You have a change in temperature at a constant. You evaporate or condense at a little bit changed temperature, but at the same or a constant pressure. So that's what's called glide. But with non-mixed refrigerants, you will condense or evaporate along these isotherms. Those lines are also indicated in this pH diagram. We also have isentropes. These indicate equal entropy of the refrigerant. These are used, so let's say you have your compressor, you start down here at this point, and you compress, you increase the pressure. 100% perfect loss-free compressor will then compress along this isentrope line. Of course, we always have losses in the compressor, so that means you will not compress along this line, but what we can use it for is calculate how close we are to this line, and that will give us the isentropic compressor efficiency. And this is what's represented in the ClimaCheck system. So in the background, we are calculating, okay, if we compress from this point to this point, we can then calculate how close are we to compress along an isentropic line. So if we then add the vapor compression cycle into the pH diagram, it will look like this. You have the low pressure, you have the pressure here, so you have the low pressure here, you have the evaporation, you are moving from left to right, you are adding energy to the refrigerant. You evaporate until you have 100% vapor, and then from this point to this, you have the superheat, and then you enter the compressor. You compress. You can see here that you have your isentropes here, but the compression is going here. So you have a difference here, and that's the isentropic compressor efficiency, the difference. And then you have in the condenser, we remove energy, so then we move from right to left. When we come here, you have 100% liquid, and then we move a little further to the left, which gives us the subcool. So the difference from here to here is the subcool. Then we enter the expansion device, and in this expansion device, no energy is added or removed, but we decrease the pressure. So then you can see you have a straight line or horizontal line going straight down here, and you're back at the low pressure in the evaporator. As I mentioned, this is not displayed in the ClimaCheck system anywhere, but it's doing this, the calculations are based on this in the background, so it's good to have at least an understanding of what is happening in the background. If we then look at cooling and heating capacity, I said we had the evaporation and the condenser here, and I said that moving left to right or right to left, we are either adding or removing energy. This means that we can now see or estimate the cooling and heating capacity from this pH diagram. So from this point here to this point here, which is the suction on the compressor, you have your cooling capacity. From this point here, which is the suction temperature, to here, which is the discharge, you have the added compressor power, or the energy added from the compressor. And then from this point here, we go from right to left, we remove energy, and then this part here is my heating capacity. So then we can see our different parts and the heating and cooling capacity in the HLP diagram. As I already mentioned, we also have, we can see the superheat in this diagram. So the difference here from this point, which is from where I have exactly 100% vapor, and then I superheat that vapor, I increase the temperature, and then to this point, which is the suction temperature or suction into the compressor. Difference between here is my superheat, and then if I look here, from my line with 100% liquid, I can then subcool that liquid, lower the temperature of that liquid, and that will what gives me the subcool. So I can in this HLP diagram see my subcool and superheat. So why do we have this superheat and subcool? And well, of course, superheat gives a protection to the compressor. The compressor cannot work with liquid, it needs vapor. So the superheat ensures that you don't have a liquid entering the compressor. And for the subcool, the most expansion devices need 100% liquid to work properly, so that you need some subcool to get 100% liquid at the expansion device. As we will see in coming slides here, we will also see how superheat, a little bit on how superheat and subcool influence the performance of the system. So if we start with superheat, typically the effect on COP, you can't really tell. It depends on from system to system what superheat does to the performance, the COP of the system. And what you can say is that you need superheat, as I mentioned, for the compressor. The compressor needs some superheat. It cannot work with liquid, so to protect the compressor you need superheat. But superheat also causes higher discharge temperature. So in most systems you would like to have your superheat as low as possible, but still have a stable system. We come back to this. And in many systems, superheat is not useful. So you have your evaporation or your cooling capacity. You take that out from the evaporator, but in many systems, most of the superheat is caused in the suction line between the evaporator and the compressor, and that is not useful. So in many systems, superheat is not useful. It will not give you any more cooling capacity. If we look at subcool, the effect on COP is in most cases positive. So if you add subcool, you can see it in this picture, that if you add subcool, you're adding the length of this line here, which means you have given away more energy from the refrigerant, which in turn will increase both the heating and cooling capacity. So subcool is positive in most systems, but to a certain point. So at some point, typically to increase subcool, you add refrigerant, but at some point, when you add refrigerant, your condensing will go up, and that will influence the COP more. So the bigger temperature or pressure lift here, the bigger pressure difference will then cause the COP to go down, and that will then cause a negative impact on the performance. So subcool is positive until you start increasing the condensing. Then it's not positive anymore. We'll come back to this in another part of this training. I already touched this, mentioned it, compressor efficiency. Of course, the compressor pumps vapor and keeps the pressure difference between the evaporation and the condensing. The compressor efficiency, it differs with different operating conditions. So if you're measuring your system in the summer or in the winter or different operating different loads, basically different operating conditions, your compressor efficiency will differ. But in the HLOP diagram, we have the compression here, from the suction to the discharge here. We have our isentrope lines here, and as you can see, if you had 100% loss-free compressor, you would compress the refrigerant along this line here. So you would start here and then up at this point here. But in reality, you start here and your discharge will be here. The difference here is your compressor efficiency, and that's one of the key values that the ClimaCheck system calculates and presents for you. Often on compressors, when your compressors start going down in performance, you will see this very early on the compressor efficiency. You can see this long before you have a complete failure of the compressor in many systems. So this is a good value to look at. We'll come back to that in other parts of this training. So now we have looked at the thermodynamics, a little bit on the thermodynamics in the HLOP diagram. So what is ClimaCheck doing then? How are we calculating the cooling and heating capacity? We looked in the HLOP diagram. I said we had the enthalpy difference over the condenser and the evaporator, and that we had the enthalpy difference then. We are measuring that. But to get capacity, to get heating and cooling capacity, we also need the mass flow. So we need the mass flow in this refrigerant circuit. We do not add a mass flow meter. What we do is that we're using the compressor as a mass flow meter. We know we are measuring electrical power input to the compressor. We know how much power we are adding. We know the enthalpy state here. We know the enthalpy state here. That means with the enthalpy difference between that point and the power input that we are measuring into the compressor, we can then calculate the mass flow over the compressor. And the mass flow in this circuit will be the same in the whole circuit. So of course the pressures and temperature are different, but the mass flow will be constant in this circuit. And when we have the mass flow here, we have the mass flow in the whole circuit. That means we can then calculate the heating capacity and the cooling capacity of the system. So that's very briefly what the ClimaCheck system, or how we are calculating performance on these systems with the ClimaCheck system. Some examples here on different types of systems. We have just looked at the very simple, just evaporator, condenser, compressor so far. Here we have some examples with HLOP diagram, how that looks in the HLOP diagram. To start right here, we have a system with a desuperator. So we have added another heat exchanger here on the high pressure side. We have the desuperator, and then we have the condenser. So in the HLOP diagram, this looks the same. On this part, you have the evaporation, the compressor, but then this first part here will where we start to decrease the energy. We are removing heat. That is done in two different heat exchangers. So this first part would be the desuperheater, and this part here is the energy in the condenser. And now you can see that just by adding this temperature sensor here, we can then calculate how much heat we are removing with the desuperheater and how much heating capacity that is in the condenser. So then we have the heating cap, of course, total heating capacity, but also divided over the desuperheater and the condenser. A system with a subcooler would look like this. Again, very similar to the simple circuit, but you would then have the condenser on this part, and then we're adding another heat exchanger here that gives you extra subcool. So from this point here to this point here, we have the subcooler, and then we add another temperature sensor to know where this point is. I mean, how much of the energy is removed in the condenser and how much is removed of the subcooler. Suction gas heat exchangers are quite common as well. This heat exchanger, this is an internal heat exchanger. It will, at this point, it will have added some superheat, and at this point here, it will have added some subcool. So if we look in the H-log-P diagram, this part here would be on the suction line. So from here to here, we are adding some superheat. We have the compressor, we have the condenser, and then we go into this suction gas heat exchanger. At this point, we are adding some subcool, and then we have subcool, the subcooled liquid after the heat exchanger over here. So that's that point. And then we go down to the evaporation. Even though this is adding subcool and superheat, this is just an internal heat exchange. So the amount of superheat you add here will be the same amount of energy that is adding subcool here. So if we look externally on the system, this heat exchanger will not add any heating or cooling capacity, but in some systems it's preferred to have this extra subcool and extra superheat. But it will not add any cooling or heating capacity if you look at it externally on what you are heating or cooling. But on this type of system, we also there are still just two pressure levels, and we add some temperatures, and we can measure on that with the ClimaCheck system. This is a type of open economizer. Now we are moving into the type of system that has more than two pressure levels. So as you can see, you have three different pressure levels. Sorry. We start up here. You have the condensing, of course. You have the condenser here. You come out of the condenser to this first expansion valve or expansion device, which takes the refrigerant down to an intermediate pressure in between evaporation and condensing. Here it separates the refrigerant, so the liquid refrigerant will go down here to the main expansion valve, and a small part will go as vapor to an economizer port on the compressor. So if we look at the H-log-P diagram, this is going to the expansion device, this is going to the economizer port on the compressor. And this gives some extra subcool, as you can see here. We are moving to the left in the H-log-P diagram. We come down to the evaporation, and then you can see that we have an added cooling capacity, or this line is longer. If we didn't have this economizer, we would have gone from this point straight down here and then evaporated. But now we are moving all the way from here to here. So it gives some added cooling capacity. It also cools down the compressor because the compression is done in 2 stages. So as you can see here, you have the first stage here. This is done internally in the compressor. So you come here on the suction line into the compressor. It compresses up to this intermediate pressure. At this point, the vapor from here is mixed with this superheated vapor from the first compression. It cools it down, and then it goes into the next compression and goes up to the condensing pressure. So the compression is done in 2 stages or 2 levels with some done in two stages. All right, and so that was just some examples first of all, on what the HLP diagram is, and then some examples on different systems and how they looked in the HLP diagram. The reason why we want to show you this is because it gives you better understanding on what is happening in the background, and hopefully it gives you a better understanding on what you need to measure and why you need to measure it. And we come, as I mentioned, we come back to this compressor efficiency and different types of systems and how to measure them in other parts of this training. So thank you for your time, and I hope this was useful for you. Thank you.